So in the last lecture, I was talking about Barlow Twins that I was saying is very simple. And now we're gonna be talking about another important article that is written in 2023, which is called Guarding Barlow Twins Against Overfitting with Mixed Samples. Because it overfits very easily. So how can we avoid it? Self-supervised learning aims to learn transferable feature representations for downstream applications without relying on labeled data. The Barlow Twins algorithm, renowned for its widespread adoption and straightforward implementation compared to its counterparts like contrastive learning methods, minimizes feature redundancy while maximizing invariance to common corruptions. Optimizing for the objective forces the network to learn useful representations while avoiding noisy or constant features, resulting in improved downstream task performance with limited adaptation. Despite Barlow Twins' proven effectiveness in pre-training, the underlying self-supervised learning objective can inadvertently cause feature overfitting due to lack of strong interaction between samples, unlike the contrastive learning approaches. So from their experiments, they observed that optimizing for the Barlow Twins objective doesn't necessarily guarantee sustained improvements in representation quality beyond a certain pre-training phase and can potentially degrade downstream performance on some datasets. To address this challenge, they introduced mixed Barlow Twins, which aims to improve interaction during Barlow Twins training via linearly interpolated samples. So here it is assessing the representation quality while k-nearest neighbor accuracy in the test set during self-supervised learning training and training set for information maximization based Barlow Twins. And you compare it with SimCLR that I've explained in a different video. So you see that you can see the k nearest neighbor top 1%. And here is the schematic of the proposed mixed Barlow Twins. So A is the original Barlow Twins algorithm that used this cross-correlation matrix here. But here they add something more in their model. They propose mixed-up regularization technique. This is a regularization technique that they also consider this. So they call it mixed-up regularization technique because it prevents the Barlow Twins from overfitting and to further enhance the representation quality. So just a quick overview of Barlow Twins that I discussed in the previous lecture. First, we calculate this cross-correlation matrix. And you know the first term in the loss, if you write the loss, then the first term aims to equate the diagonal element. This enforces invariance in the embedding, making them resilient to applied distortions. The second term in the loss that I discussed was that the second term strives to equate the off-diagonal elements of C to 0. So while Barlow Twins algorithm boasts a straightforward design and a capacity to learn valuable representations for downstream tasks, we have observed a critical phenomenon, which is increasing the dimensionality of the embedding space can result in the production of lower quality representations, but also in the risk of overfitting. This behavior may manifest as the network endeavors to minimize invariance and redundancy by memorizing individual samples. So it's very bad because here we are doing overfitting. This issue, somewhat surprising, was neither acknowledged nor reported in the original Barlow Twins study, which primarily emphasized linear evaluation results conducted on the extensive ImageNet dataset. However, our experiment, conducted on smaller to medium-sized datasets such as CFAR10, CFAR100, provide compelling evidence of the Barlow Twins' susceptibility to overfitting and a generation of suboptimal representation with the expansion of embedding dimensionality. And to underscore this concern, we executed k-nearest neighbor evaluation and monitored top 1 accuracy at 5 epoch interval throughout 1,000 epochs of Barlow Twins training. And you see the results that k-nearest neighbor evaluation results on test set with ResNet 50 backbone for Barlow Twins with different embedding dimensions. For example, A here is on CFAR10, B is on CFAR100, and C is on Tiny ImageNet, and D is on STL10. But what causes the overfitting? The observed overfitting issue of Barlow Twins can be attributed to its unique loss formulation. To better understand this, let's compare the Barlow Twins with info and CE loss. I see that in many papers they compare their model with info and CE loss because it's very easily, you can easily see the theoretical structure of that, and you can compare your model and interpret the loss because it's very I can say it's like a template that or a reference that you can compare your model. Theoretically, you can analyze it much easier than any other paradigm. So that's why we use the loss info and CE loss in this form. We call it, the first term is called similarity term, as you see. And the second term is contrastive term. But Z sub A and Z sub B are the twin network outputs. B indexes the sample in a batch. I indexes the vector component of the output. And tau is called temperature. I've seen some articles that emphasize an influence of this temperature on alignment and uniformity. And as we can observe, the info and CE loss aims to maximize the variability among the embeddings by increasing the pairwise distance between all sample pairs. In contrast, Barlow Twins loss operates differently. It focuses on decorrelating the components of the embedding vector rather than emphasizing the distance between samples within a batch. The distinction lies in Barlow Twins' approach, which results in no or less interaction between the samples in a given batch. As the embedding dimension grows, it leads to considerable increase in the total number of trainable parameters. This expansion can potentially lead to overfitting, where the optimization process predominantly involves memorizing the samples rather than substantially improving the quality of the embeddings. This deviation from encouraging sample variability to focus on decorrelation might be a contributing factor to observe overfitting in Barlow Twins. And guarding Barlow Twins from overfitting. So to achieve this, we propose to incorporate an additional regularization on top of Barlow Twins' loss function, which promotes interaction between the samples in the batch. The new regularization term is inspired by mixed-up regularization in supervised learning, but adapted to the context of self-supervised learning, aligning with Barlow Twins' loss formulation. So the proposed mixed Barlow Twins first generates a batch of mixed samples. So these are mixed samples, but it's just a linear interpolating between YA and YB, because YS is just a shuffle of B. Then, since both YA and YB consist of different views from the same image, we first shuffle to ensure the linear interpolation predominantly involves different images. And this process can be mathematically written like this. But here YS represents the shuffled batch of images obtained by shuffling images in YB. In PyTorch, in Python, I use import random, and then I shuffle that very easily. And we sample from beta distribution, lambda draw from beta distribution, the parameters alpha and alpha. Then we feed YM through the encoder and projector to obtain their normalized embeddings centered along the batch dimension. And here denotes the network. Subsequently, we compute the cross-correlation matrices between the mixed embeddings and the unmixed embeddings. And T denotes the matrix transpose. And then we can determine the ground truth cross-correlation matrices. And here, this shuffle star is shuffling embedding in the same order as before. The mixed-up regularization is designed to align CMA and CMB with their respective ground truth cross-correlation, because we know the ground truth cross-correlation, so why not make sure that they don't deviate from that too much? So this is a good way for avoiding overfitting. Very natural way, because we know the ground truth. And the final loss, you just add the regularization term. Of course, this hyperparameter makes a trade-off between these two different objectives. And finally, you can easily compute embeddings after augmentation, and then you normalize along the batch dimension. Like previous lecture, you calculate cross-correlation matrix like this, because it's matrix multiplication of these two vectors, and then you have the loss, which is C minus identity to the 2, and then you calculate the loss. So for the mix-up regularization, we just need to add this mixture regularization, because this is in this article. You just add these new lines. First, you create these mixed samples. You compute mixed samples embeddings. Here you compute the embeddings, and then here you calculate cross-correlation matrices, those two matrices that I told you for A and B. And then because you know the ground truth, you can just say it shouldn't go too far from the ground truth. So this is a good way to regularize and make sure we don't overfit. And then this is the previous lecture. Now we just add this regularization term, so to get the loss, and we backpropagate this loss, the total loss, not just the Barlow Twins loss.